You're listening to Worth Electronics' What's Up radio podcast, and each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast. Well, today we are talking ferrites, specifically in regards to EMI, or electromagnetic interference. Now, EMI is a hot topic if you are designing any application because you need your electronic to function properly in its environment. So today's broadcast is based on a previous webinar. We are headed down to our technical team in Mexico. Oscar Gonzalez is a technical chat navigator at Worth Electronic Online. Oscar recently presented a very popular webinar, EMI 101. In this first half of the presentation, Oscar covers the basics along with an overview of EMI, and then he goes into details on chip bead ferrites and reading the data sheets associated with them. Enjoy this presentation of the first half of EMI 101 with Oscar Gonzalez.
Hello, and thank you for joining today's webinar about EMI 101, in which I will focus on ferrites. My name is Oscar Gonzalez with Worth Electronics, and my intention today is to go over the basics of EMC, also understand some important characteristics about ferrites and how to choose and implement one in your projects. At the end of this presentation, you will be able to ask any questions you may have about the topics exposed in this presentation, so let's go ahead. So the purpose of this webinar is to give you an overview of what EMC is and how it may concern you and your company. Once we understand what EMC is, we will then talk about chip bead ferrites and understanding the information shown in their datasheets. Next, we move on to defining losses and the details of insertion loss calculation. And finally, we will finish up with a discussion about clamp-on ferrites. So first of all, we need to identify the differences between EMI and EMC. So every electronic device emits EMI, or electromagnetic interference. How that affects your device and other electronic devices is where EMC comes in. The EMC, or electromagnetic compatibility, is concerned with how well your product interacts with other products within its environment. So as you can see from the picture, the world is a busy place and is filled with EMI. Your job here is to make sure that your device does not cause any unintentional failures to other devices, while at the same time protecting your device from the EMI caused by others. So in short, in order to be electromagnetically compatible, you need to prevent emissions and have high immunity. So keep this statement in mind as we move forward in this presentation. There are many types of electronic devices in the world that provide many types of different applications. The level of the products goes from very simple to very complicated. And with that being said, the impact of a failure of one of these devices may be harmless or may be life-threatening. So therefore, there are many regulations for EMC to ensure the safety of electronic devices and make sure there aren't any unintentional failures caused by EMI. IEC is a worldwide standard and EN is an European standard. I am sure that you have already heard about them before, so we won't get into the details of each standard today, but I just wanted to show you that there are very specific regulations for several industries. For example, here we have medical equipment, we have industrial equipment, information technologies, white goods, and so on. So it is very important that you are aware of what regulations your product needs to meet in order to bring your product to the market. It is not up to the manufacturers of EMC components, such as Worth, or EMC labs to tell you what standards you need to meet. So you will need to know this by yourself when getting your product tested at the EMC lab for certification. The EMC lab may be able to point you in the right direction, but at the end of the day, it is your responsibility. So there are a few different types of EMI. Understanding each one of these will help you identify what might cause any EMI issues that you will encounter in your project. So first of all, we have conductive coupling, which is a physical coupling path that is formed by a direct contact. An easy example is a cable, or it may be a wire, but keep in mind that it can also happen with any trace of on a PCB or even a metal enclosure. Then we have capacitive coupling, which is specific to an electric field. This occurs when a varying electrical field exists between two adjacent conductors. So for instance, when you have two plates with a potential difference separated by any space, essentially what you have is a capacitor. Then we have inductive coupling, which is specific to a magnetic field. This occurs when you have a varying magnetic field between two parallel conductors. This causes parasitic induced voltages. And last but not least, we have radiative coupling, which occurs over the air. So every trace on a PCB is a potential antenna, and therefore a potential coupling path. Typically in high voltage applications, capacitive coupling will dominate, whereas in high current applications, the inductive coupling will dominate. And now I want to show you an example of what not being protected against EMI causes in your products. So here we are using an old picture as an easy example of what EMI looks like. So on the left, you see a picture as taken from an old television. The picture looks good and it does not show any noise problems. But because this old television was not designed with EMI in mind, it is susceptible to failures caused by the environment that it is operating in. So the picture on the right shows the result of the interference. To put this slide into a real-life scenario, you have to envision yourself watching TV. While watching your show, someone has decided to vacuum the living room, for example. So the result of the EMI emitted by the vacuum affects the circuitry of the television, resulting on the distorted screen that you see on the right. So luckily, standards have now been put into place to prevent this situation. As stated previously, in order to be electromagnetically compatible, you need to prevent emissions and have high immunity. Emission is concerned with the EMI leaving your device, and immunity is concerned with EMI entering your device. So there are also two types of each of these. We have conducted and we have radiated. So conducted is a direct connection like a wire or a cable, whereas radiated means through the air, which is in an electromagnetic field near to your device that may affect it. So just to be clear on the types of interferences, a conducted emission is EMI leaving your device through a direct connection. A radiated emission is EMI leaving your device as radiation through the air. The conducted susceptibility makes reference to the immunity of your device to not allow EMI to enter through a direct connection. And last but not least, the radiated susceptibility means the immunity of your device to not allow EMI to get in as radiation through the air, pretty much. So as mentioned previously, there are a number of EMC regulations out there. Two that we run into quite often are CISPR 22 and FCC 15. I will not get in a detailed explanation about this. This is just a quick overview of each one. So CISPR 22 is a standard applicable to the European community. It tests for conductive noise at 150 kHz to 30 MHz, and it tests for radiated noise at 30 MHz to 6 GHz. In the other hand, we have the FCC15, which is a standard applicable to USA. It tests for conductive noise at 450 kHz to 30 MHz, and it also tests for radiated noise at 30 MHz to either 40 GHz or the fifth harmonic of the highest frequency of your circuit. So anything above 10 MHz is where you should start considering that there is a common mode noise issue. The chances are higher that it is common mode noise above 10 MHz, but of course this is not a guarantee. It is possible to have differential noise above 10 MHz, but this does not happen very often. So to dig into CISPR 22 and FCC15 a little further, this slide shows the conducted and radiated tests performed at the same frequencies, but breaks it down into Class A and Class B. Class A is for commercial, industrial, and business environment equipment, and the Class B is for residential environment equipment. The tests for the Class A are more stringent because of the environments they will be operating in. So in terms of similarities, the conducted and radiated emissions limits specified in the CISPR 22 and FCC 15 are close to each other. So in this way, it is possible to meet both the standards easily for the certification process. So now let's talk about the details of chip-bit ferrites and how to pick out the important specifications from the datasheets. So we will talk about how what they are, how they work, picking out the right part from the datasheets, and how to use them. So a chip-bit ferrite is nothing more than an inductor, and it is used to remove unwanted noise at high frequencies on supply voltage lines, also ground planes and data signals. So if you remember the law of conservation of energy, you remember that energy cannot be created nor destroyed. It can only be converted. So that is exactly what a chip-bit ferrite is doing in this application. It is transforming unwanted signal energy into thermal energy. And in other words, it is converting the unwanted signal, aka the noise of your circuit, into heat. So in order to maximize impedance of an unwanted signal, you need to choose the appropriate material that has the best characteristics to absorb the specific frequency that you're trying to attenuate. This material must be non-conductive to ensure it does not short to the core. All of Würth's chip-bit ferrites use nickel zinc because it is a non-conductive material. So what you end up with is a frequency-dependent resistor. The picture on the right shows you the parasitic of a chip-bit ferrite. Here we need to always be cautious of this because a chip-bit ferrite has inductance, it has capacitance, and it also has resistance. So we will discuss this in more detail later in the presentation. So this slide shows you an X-ray view of a chip-bit ferrite. Keep in mind that the windings are not insulated and the core is non-conductive. So as you can see, the winding of the high current chip-bit ferrite needs to be thicker in order to handle higher currents, and therefore is wound horizontally, just to have more space for the large winding. The high frequency chip-bit ferrite needs to maximize the number of windings, and therefore it utilizes the space it has by being wound vertically. So due to the reduction of the effective area of the conductor, less current can be carried by the high frequency chip-bit ferrite in comparison to the high current chip-bit ferrites. The main point that I'm trying to show you here is how these two types of chip bit ferrites are manufactured differently just to provide their intended end use. So if we base on physics, we can understand how inductive reactance works. So if we base this explanation on the picture shown at the right of this slide, we need to identify the primary current flowing through the inductor, which is marked with a red arrow. Also the magnetic field generated around the turns of the inductor, colored in blue, and the resulting induced current from the changing magnetic field, colored in green. So inductive reactance is the result of a primary current fighting with the induced current in a helix type of winding. This phenomenon happens due to Lenz's law. This formula, you can actually see it at the bottom left of this slide. And as you can see, the inductive reactance, or XL, is a function of frequency and inductance. So this is just a simple explanation of how inductive reactance works in an inductor. And so as mentioned previously, a chip bit ferrite has inductance, it has resistance, and it has capacitance. You can see these characteristics shown in the blue, green, and yellow areas of the graph on the right of this slide. So this is what you see in a typical datasheet of a chip bit ferrite. I would like to remark three curves that are shown here. So first we have C, which is the impedance. This is the main curve of the graph. You also have XL, which is the inductive reactance. This is colored in the graph as a blue dotted line. And you also have the resistivity, which is not the DCR. This is just the resistivity of the part. So this is colored as a red dotted line in the graph. So now the crossover frequency is where the inductive reactance and the resistivity meet, shown here as the red and blue dotted lines, of course. So below the crossover frequency, the inductive reactance is higher than the resistivity, and therefore the part is better used as an inductor for energy storage purposes. Above the crossover frequency, you see more resistivity, and therefore this part is better used as a filter at those frequencies, up to the self-resonant frequency, or the SRF of the part. Then we have the self-resonant frequency, which is the highest point where there is no inductive reactance and your impedance and resistivity are at its highest point. The main purpose of a chip bit ferrite is to block unwanted AC noise frequency. So anything over the SRF will become capacitive, which passes AC and blocks DC. So therefore, if you need a filter, you do not want to be in the capacitive region of the chip bit ferrite. So after the self-resonant frequency, this device will not work for our circuit. To block noise effectively, just make sure that you choose a chip bit ferrite with a high impedance in the range of frequency where the noise is located, so it is attenuated properly and does not affect your useful signal. As with other magnetic technologies, it is very important when choosing a chip bit ferrite to pay close attention to heat. As mentioned previously, we are converting an electrical energy to a thermal energy and dissipating it as heat from our circuit. So there will be a temperature rise of the part, and we must also be aware of the ambient temperature in which the part will be used. So sometimes it will be necessary to derate the current because the core is temperature sensitive. For commercial grade products, the core material we use has a maximum operating temperature of 125 degrees Celsius. Because above 125 degrees Celsius, we come close to the Curie temperature and the permeability drops down to 1. So the Curie temperature is where the material starts to lose its magnetic properties. So we must take care of the temperature of operation of our component as well as the current flowing through it. Here is an example of a product that has an ambient temperature above 85 degrees Celsius. So we specify on our datasheets a 40 degrees temperature rise above ambient temperature when used at 5 amps. So remember that a part used in an 85 degree ambient temperature with a 40 degrees temperature rise will result in a maximum operating temperature of 125 degrees Celsius. And we cannot exceed the recommended maximum operating temperature, so this is our limit of operation. In this case, we have an ambient temperature of 105 degrees Celsius. So when we add in the 40 degrees temperature rise, we will be exceeding the 125 degrees maximum operating temperature, and therefore we must derate the current of the part. According to the graph shown on the right, we see that at 105 degrees Celsius, we must derate the current by 50%. At 2.5 amps, you get a 20 degrees temperature rise above the ambient temperature. So the result of an ambient temperature of 105 degrees Celsius and a 20 degrees Celsius temperature rise puts us safely at the 125 degrees Celsius maximum operating temperature. We specify our chip bit ferrites with zero bias. This is something important to keep in mind. So therefore, we only show you the impedance that you will get with no current flowing through the part. So for example, this slide shows 330 ohms of impedance at 0 amps. So if you were to add current flowing through the part, you will be saturating the core. If you saturate the core, the impedance drops and the frequency shifts. We do have actually LTSpice models, but only for our high current chip bit ferrites, so you can run your simulations. So how you need to choose a chip bit ferrite? Well, the answer is pretty much that it depends. So based on your application, you need to take into consideration the frequency range of the noise, also the source of the noise, the amount of attenuation needed, the environmental and electrical parameters of the circuit, and as with everything else, space and cost. So it becomes a trade-off between all of these considerations based on the priorities of your situation.
This podcast was taken from a Worth Electronic webinar. To view the materials and replay the webinar on demand, click the link attached in this podcast. You can learn more about EMI components and find our complete portfolio by visiting Worth Electronic online. Look for this episode in our profile or click the link available in this podcast. As I mentioned before, our presenter, Oscar, is a technical chat navigator at Worth Electronic Online. You can chat directly with Oscar by clicking the chat icon at www.we-online.com. You're listening to Worth Electronics' What's Up radio podcast, and each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast.